All right, good afternoon, everyone. Hopefully, this is working all right and everybody can see my screen. Um, my name's Michael Urban. I'm the vice chair of SEI, and thank you for attending our meeting. We have a great presentation today. It's the I-95 CAP, Central Axis Philadelphia. Um, I'm really looking forward to this presentation. So sit back, relax, and enjoy the next hour. Just in the meantime, I just want to get over some housekeeping. This is just our board members. Our chair Keith Merle. Unfortunately, he cannot be here, so as vice chair, I'm taking over for today's presentation. Then we have Colin, Greg, Nikki's our past chair, Alex, Nate, and Justin. So first, I just want to thank our sponsors from our previous golf outing last year. We raised a lot of money. We were able to support three college students, give them some scholarships. They were really excited. We're really happy that we are able to do that as an organization, and along with the members to help these students out because they are our future. So we're really excited that you were able to participate and contribute to the golf outing. This coming up May 9th, actually, we are going to continue. It's been a success. It's been very successful. We're going to continue with this and keep on having a day of golf, good weather, get out, talk with our colleagues and our peers, and then at the same time, contributing to, our future with these scholarships. So keep an eye out. We will be sending a save the date shortly for the golf outing, as well as sponsorship opportunities. So be the next to sponsor the actual SEI scholarship. As I had mentioned in the email, this meeting is being recorded. Um, so just keep that in mind. Your microphone has and camera has been disabled as through this town hall meeting. So there is the Q&A function. So when asking questions, feel free to ask questions during the presentation. Use the Q&A feature in there, and we can and at the end of the presentation, we will ask the questions to I'll ask the questions to the presenter. So if you have something in mind, feel free to put it in, and at the end we'll make sure we get to your question. Here is a link to our website. Check it out for all the latest events that we have coming up. You can always email us at phillysei@gmail.com. And as mentioned several times this year, we are now on LinkedIn. So we have the QR code right there. If you want to quickly scan it, it'll take us right to our LinkedIn page. Follow us. We'll use it regularly to update with events, tech meetings, everything SCI coming up. So be sure to follow us. Speaking of upcoming events, next week, actually, we're really happy to announce that we're going to do a winter social. As you may have known recently, we have switched over to virtual meetings, because it's been tough, with this climate, getting people together with everybody's schedules, being at home, being at work. So, us being able to do these technical meetings, at a cheaper rate, it helps us, reserve funds that we can do these winter, these other events such as our winter social, and that still gives us the opportunity to get together as a community, as this structural engineering community, and get to talk and outside of work, outside of technical presentations, but with you attending these meetings, that helps us fund these events. So we're definitely looking forward to keeping these up. So we'll have our winter social, and then obviously with our spring golf outing. And then also next month we have the DVGI joint meeting, SEI DVGI joint meeting. So keep an eye out for those. Another one that's actually I'm really excited for is this year we'll be heading over to Swarthmore College on the 25th to do a panel for students. So if anybody is interested in sitting on that panel, it's a great time to, explain to, how you are as professionals in this structural engineering profession to these students. It's for the 5 different colleges in the area. So looking forward to that. So again, if you have any interest in doing that, reach out to any of the board members or the Philly at SEI, phillysei@gmail.com. And then just two more events. We'll have our SEI Philly, another virtual event, Structural Strengthening with FRP. And then we'll have a in-person event. This is our multi-tech event with ASCE. And it'll be held this year at the Inn at Swarthmore in April. And so keep an eye out on the different presentations that you'll have for that. So just as I mentioned, the Winter Social, it's next week. It's going to be a great time. It's only $20. You get a beverage ticket, appetizers, and just hanging out and talking with everybody. So, I'll keep it up for a second. Scan the QR code. It'll take you right to the registration page. $20, and it's going to be a great time. Looking forward to it. It is at Workhorse Brewery, and I guess it's Conshohocken, I guess it's considered. Or Bridgeport right there. So in the area, it's going to be a fun time. And then just the SEI DVGI meeting later this month as well. If you want to scan that QR code, and that will get you to the registration page for that. So without further ado, thanks for listening to me talk about the chapter. But today's speakers, we got three great speakers talking to you about this CAP project. John Philippe is a senior engineer at Panonie's Philadelphia Transportation Division and the engineer of record for this project, the bridge structure. So he received his bachelor's degree in civil and architectural engineering with his structures concentration from Drexel in '93. And he has an associate's degree in architectural design and drafting. He has 31 years of experience with transportation structures. And he was previously employed by Whitney, which is now WSP, and the City of Philadelphia Streets Department. So definitely in this area. John's experience has ranged from steel to concrete bridges of various types, underground structures. And I'm not sure if anybody else wants this, but if it was snowing, he would be skiing right now. So luckily it's not, and he's here to give this presentation to us. So next, we have Julie Lutzke. She serves as the senior project engineer in Panonie's Philadelphia Structures Division. She received her architectural engineering degree from Penn State. Sorry about that loss. In 2008, and has 17 years of structural design experience with concentrations in new building construction and adaptive reuse. Julie has worked on a variety of projects ranging from large-scale new construction and the small-scale renovations. So for the I-95 CAP project that she'll present today, she was the lead structural engineer for the park structures. Jesse Gormley, he is a senior engineer in Panonie's Philadelphia Transportation Division. He received his bachelor's degree in architectural engineering and his master's degree in civil engineering with the structural concentration from Drexel. So a lot of Drexel representation here. He has 15 years of experience with the transportation structures on projects of varying scale and ranging from new design to rehab. And so for this project, he was the structural task lead for the substructure and foundation design of the Park Bridge. So got a great presentation. So sit back, relax, and I will now turn it over to our speakers.
Thanks, Mike. Quick screen share here. Ready to go. Turn that off. Wonderful. Hopefully everyone can hear us. Just get confirmation of that real fast, Mike, if you don't mind.
I can.
Perfect. All right. Thank you, everybody. Thank you to the SEI Philadelphia chapter for hosting us today. As Mike mentioned, we're going to talk to you about the I-95 section CAP project. CAP is Central Access Philadelphia, focusing on different structural elements for the main park site. Mike did a great job reading those way too long bios we provided. Appreciate your patience. As far as the agenda today, so I am going to introduce the project, go over some of the goals, the background, the history of the site we were dealing with, and then I'm going to hand it off to John first to talk about the park bridge design, and Julie to then handle the other park structures that were part of the design. We will leave some time at QA in the end. I think the important takeaway here is you really want to hear from these two today. You don't actually want to hear from me. Before we get into the details, we did want to thank and acknowledge the project team here. This is the design side. First, our partners, PennDOT and FHWA. They both played project lead as far as the infrastructure design maintenance. Infrastructure in this case would be the bridge and I-95 below it. PennDOT will ultimately own the bridge. The Delaware River Waterfront Corporation is going to be responsible for park programming as well as management and maintenance, whereas the city of Philadelphia will serve as park owner moving forward. They're great partners on this project. We really appreciate their guidance here. We, representing Pannoni, were the design team project manager and the prime for the contract, but we could not have done everything we're going to be presenting to you today without the help of all of our teammates. You see many of them listed below. We'll probably give some specific shout outs as we go, because a couple of these folks were very involved with some of the structural work we're going to talk about, but we really appreciate all of them. Again, I mentioned this is the design team. The project has been awarded to a contractor. It's going to be Buckley & Co. So far, they've been, excellent moving the project forward in construction. We're excited to, continue future presentations featuring more of the construction elements too. We will be focused on design today, but between Buckley and the CM team with Hill and many others involved on that side too, we're very thankful. All right. Quite sure everyone is familiar with where Philadelphia is, but we thought the graphic on the left was helpful. The pink line, bull pink line, is representing Interstate 95, going from Maine all the way down to Florida. You can see we're in the middle, right in that densest corridor of 95 between New York and DC. Zooming in on the right, you can see a red box outlining the project footprint. This is a primary project footprint. There were elements outside of this, but this is really we're going to be zooming in on moving forward. Before we get into the specifics of our project, I want to talk a little bit about the history in this area. Looking at these photos, this is early 20th century at the waterfront, and the important aspect of this is, if you look at especially the two photos on the left, you can see all the people. You can see the vehicles, you see trolley cars, horse-drawn carriages on that bottom photo. On the right, you can see the elevated subway. Early century through World War I, even through World War II, the waterfront in Philly was a bustling hub for commerce. It was an active port, and really had a lot of people moving around in it. But as we approached mid-century, we moved away from some of the commerce and manufacturing and more towards industrial state. And with that shift towards industrial work in this area, a lot of the properties started to become vacant, which made this area a prime target for other development. And you see the photo on the left, circa the late 60s into 1970, construction of the Penn's Landing site, which is where we're going to focus on for our conversation today. You can see how we actually had to build out into the river to construct that area, the basin at the bottom of it. And then in the photo on the right, you can see the beginnings of the construction of I-95. At the top of the photo on the right, you can see the Penn's Landing site in the background there. I think the unfortunate part with the development of I-95 is in order to construct it through this area, many homes, many neighborhoods needed to be demolished to accomplish that. Over the course of this project, we had the privilege of talking with some of the families who were displaced during that time and got to hear their stories. And I think the whole team really took a lot of that to heart in terms of being sure that we were approaching the development here in the project in the right way and engaging as many stakeholders as possible throughout. Fast forward to what we're calling the existing condition. It's in quotes because the whole site on the left, the Penn's Landing, many of us have known and loved for the last 50 years or so, is now demolished. Construction is underway for the new structures that we're going to be showing you. But yet we thought it was an important capture of what the infrastructure that was out there was. And from here, we'll pivot to 2011. In the middle of that window, while the existing park spanned over 95, while there were some pedestrian bridges there, still there was a grander vision launched as the master plan for the Central Delaware to improve and develop this area, try to increase access and bring people back to the waterfront. And the part I think is most impressive about this whole thing is the stick-to-itiveness that has gone with this vision. You see 4 elements called out here that were addressed as part of the I-95 CAP project. We're going to focus in that one highlighted in green, the Penn's Landing Park today. But the fact that, a plan developed nearly 15 years ago is actually coming to reality now, I think is highly impressive. In terms of project goals, there were many, and you see the long form version of them here. I bolded the ones that we're going to address most directly with the presentation today. Numbers 5 and 6 really focus on the South Street pedestrian bridge, which I will show a photo of. I'm hoping you will get to see other presentations on that in the future, but it won't be a focal point of today's presentation. And the goals for us revolved around increasing access to the waterfront from the city, doing that by creating an inviting, open public space with landscaping that would bring people and make them want to come in to the new park space, as well as improve the visual connection to the river from Front Street. And I'll show you a graphic in a minute clarifying that one. And that last goal on the bottom was something that everybody carried throughout all the work we did. We wanted to be sure we were considering flexibility for future development and improvement in this area, both along 95 and along the Christopher Columbus Highway stretch. Oh, before I move on to this, the figure on the right comes out of PennDOT's publication 10A. I'm sure many of you are familiar with it, but we've been flashing this on screen when we get a chance because it's a great representation of what that community involvement process is supposed to be like through both planning as well as engineering and even into construction. And again, the project team is very proud of the level of input we were able to get, the community involvement that we had. All right, to provide another overview, here's an aerial of that project site I showed boxed out earlier. Mentioned there's a multi-use trail passing along the edge of the Delaware. That is the Delaware River Trail. I'm going to give a shout out to NV5, who really led the design on that element. Much of it is constructed, but the tie-ins to some of the new infrastructure going in, the South Street Bridge and the new cap structure bridge, are yet to be completed. Obviously, our focal point for today, the new I-95 cap bridge and other structures. That's what we focused on in this presentation, but it is, the largest aspect of the project, I think. It was because it is the focal point around a lot of this other work. 11.5 acres of total green space, 470 mature trees going on top. It's a large structure. Also mentioned the South Street Bridge. I'll show another rendering of this in the past because it's a beautiful structure, proposed to serve as a gateway to the whole area. And then several other aspects of the project, not really represented in this graphic, but mentioned access was key. So we're extending multimodal access to the river through the park space, but also through coordination with SEPTA and what transit routes they have leading to this area, coordinating with the city for the bicycle network, being sure there's other opportunities to get here. Streetscape and traffic calming measures taken especially along Front Street, again, to try to create an inviting access front door to the park, if you will. Traffic signal enhancements throughout, especially along Columbus Boulevard, and then improvements in traffic management system ITS work along I-95. Here's that rendering of the South Street Bridge, a really, really cool asymmetric tied arch structure. WSP led design for this, a great teammate, and I'm optimistic, like I said, that you'll get other presentations by them on this structure in the near future. Before I hand it off to John to talk about the bridge, one quick point. I mentioned the goal of restoring visual connection to the river. And I think to really spell that out, that center photo at the top, that was looking at the river from Front Street down Chestnut Street at the former park structure. And the important takeaway here is you're virtually at the river and you can't see the river. We wanted to fix that as best we could. You also see in the right, this was the frontage for the existing park along Front Street. Those retaining walls were implemented to bring soils up to appropriate depths for plantings and to support the features that they wanted to have on there. But unfortunately, they served as not only a visual block, but also, restricted access from any point along Front Street. That was something that we wanted to try to correct in our park design. Down bottom is a cross section of the bridge. It's actually the south elevation, and you can see 2 red circles. Those were vertical clearance controlling points for us. Obviously, there's some challenge in both restoring the connection, that visual connection, trying to keep the bridge profile low, while also meeting those vertical clearance requirements. But I think we rose to the challenge. Again, John will tell you more about the superstructure and how that design went. All right, before I officially hand it off to John, here's just an overview of some of the amenities on the top side. I'll leave that for a second. Julie will go in depth on the pavilion and cafe later, but we're just sincerely excited about the future of this area with all of these different features. All right, with that, I will hand it off to John.
Good. So I'm going to focus on the bridge structure, the components, basically all the stuff that you can't see when you're on that beautiful landscape structure, but all the stuff that we as engineers appreciate. So here's another overview of the area and showing the existing structures that are there right now: chestnut, walnut, and I guess landscaped bridge holding Irish and Scottish memorials. All these structures will be removed. These consist of box girders, and a lot of problems were associated with this design, especially with water infiltration. The new bridge structure will be overlaid and extend beyond 95 over Columbus Boulevard. And the terraced landscaping that you see now will all be replaced with new park, all on fill. Again, this is comparing existing to proposed cross sections. Again, the wide portion of the existing structure was a park and also Chestnut Street, and 374 feet approximately. And then there was another pedestrian bridge, Walnut Walk. All that coming out and now being one continuous 614-foot wide structure consisting of steel eye girders. I'll get more into the specifics of that later. Again, another comparison between existing and proposed structures. You see here the existing box girder bridge with 4 spans altogether over I-95, but not over Delaware Avenue. The new structure is going to extend over Delaware Ave, which is now Columbus Boulevard. So it was 209.5 feet previously, and now 363 feet approximately long. These piers and abutment / pier, if you want to call it that, are all coming out. And the base slab here and abutment 1 are going to remain, whereas abutment 1 will be modified. So eliminating the piers in the middle, the 2 piers that you see helped with lane arrangements for I-95. The existing base slab, which was a very thick concrete slab underneath I-95, was preserved as much as possible in building this new structure. And also, we found that there were some existing unknown foundations underneath all of that too, as we progressed drilling operations, right? So the interesting thing here, as I go on further here, abutment 1 was retained as much as possible and remained connected to the base slab, and that's shown in light gray here. And underneath that was a pile cap in dark gray. But in order to reuse the existing abutment, we had to modify it. So one of the things we had to do was a pile cap extension. to help resist the loads because the piles were overstressed. Additionally, we had to remove a portion of the top of this abutment and modify it to accept the new steel eye girders. And behind that, to help reduce lateral loading, we used ultra lightweight foam glass aggregate, otherwise known as ULFGA. And this helped with overturning forces. And additionally, base slab strengthening as well to help with the overstressed base slab or footing. If a base slab which acted as a footing for the abutment, WSP helped us finish this design and detail it. So many thanks to them for that. This is a view of the top of the abutment at abutment 1 here, and how much we had to remove. And you can see a portion of the box girder bridge there that had to come out. And in comparing what we had to remove with what had to go in, you can see how we had to dowel into the existing structure. And this was all permitted because we want to make sure the dowels were never in tension and there was enough compressive force on there to accomplish that. This is a slide also facing at abutment 1. And the reason I'm showing this is because I want to show how there were many utilities going through this structure. And considering how wide the bridge was, we had to accommodate lateral movement, transverse movement, not just longitudinal movement. So the utilities had to pass through, but allow for the diaphragm to move back and forth. So what I was trying to show here is that how as the structure moved back and forth, the ducts stay still, but the structure would move back and forth, and there were neoprene sponge and proprietary compression expansion joint system on either side of the ductwork to get that to work. This is something similar that we used on the Vine Street Expressway bridges, if you're familiar with that project. Another view of the ductwork passing through the diaphragm and a back wall and underneath an approach slab, which is all like threading the needle on this one. And not just ductwork, but there was also drainage from the troughs that were on the bridge. All the landscaping had to have drainage underneath, and this had to penetrate through the back of the back wall, and this was tricky because, again, we had lateral movement in addition to longitudinal movement on the bridge. So it turned out to be quite a detailing nightmare to try to get this to work, to say the least. Pier 1 on the structure was replaced. The original pier was also tied in to the base slab, which served as a footing. We wanted to do the same here with minimal, intrusion on the base slab. So we managed to build a new pier on top of the base slab by doweling it in. However, we had to check for all load cases that the dowels were never in tension, but there was enough dead load to overcome any kind of overturning forces that may have been seen. So this helped reduce cost. Pier 2, the base slab pretty much ended, and we had to support foundations of some sort. So working with Aegis, our geotechnical engineer, we determined that 6-foot diameter caissons will be the way to go on this. They were pretty deep. They averaged 90 to 102 feet just to get to the top of competent rock. And then we had to extend the rock sockets below to obtain the capacity that we needed. So those rock sockets were also 14 to 50 feet long. So the total length of caissons were 111 to 161 feet. Right now, they're preparing to do a test caisson on this. So fingers crossed. Additionally, if you can notice, there is a twin cell box culvert, which we had to avoid and span over. Right there. Then moving on to the superstructure. Loading on this bridge had to accommodate all landscaping, and we split up the bridge into 2 regions. Pedestrian region with landscaping and a vehicular region for Chestnut Street in blue, as you see here. On the landscaped regions, we don't just take pedestrian load, but also a maintenance vehicle. But then we also check the structure for the design live loads that PennDOT requires us to check, as well as emergency vehicles. And then the Chestnut Street Bridge was treated as a regular highway structure with all applicable live loads and pedestrian loads as well. Now, since this was a park bridge and the intent was to plant trees on it, that's what the troughs served, we had to accommodate those trees, and trees grow over time. And we assumed that the trees would extend 50 feet above the sound barriers. So then we had to consider all the wind load that was being applied, not just to the edge of the barriers, but to the trees as well, which then would get transferred to the bearings. So one of the interesting aspects with loading that we had to take care of on this bridge. Now, getting a closer look at the superstructure, you can see all the irregular loading conditions that we have here. In green, we have landscaping and the deck, and on Walnut Walk, mainly for pedestrians, but also for emergency vehicles and maintenance vehicle. And this is on the Chestnut Street side, again, park structure extending right into a vehicular type setting here with pedestrians and bike lane. Now, the troughs did not contribute to the structural capacity of the bridge in our design. We relied solely on the 3 girder groups that you see. So between each trough are 3 girders. These girders mostly were 47 each deep, 50 KSI steel. The girders on Chestnut Street had to be a little smaller, 39-inch deep webs. Now, STLFD was used to design all the girders, and I'm going to mention that this was a conservative method of analysis. We also did a 3D model, and this was to more accurately model the deflection of the bridge to get camber. An additional model was done just to design the troughs. And we also got a lot of help for WSP for designing the troughs. The the framing plan is quite large, to say the least. What you see in red on here are all the bays that have utilities. Now it's hard to discern what's what on here, but there's lots of diaphragms, truss support beams, and utility supports. The CSI bridge was used to model the structure. And again, it was a very large model. It took a day or two to run to get results. So it was time consuming to do iterations, to say the least. And this is one of the reasons why we created a truncated model just to design the troughs. So as I said previously, the main CSI bridge model was used to determine deflections accurately to properly camber the girders. And again, we also used a 3D model for designing diaphragms. And I'll get more into this a little bit. So the girder, a point on girder camber was, since this was not a symmetric structure, but it had like an unbalanced span arrangement, this created an upward camber in the center span. So I'm not used to seeing something like this, but this is what happened on this bridge, especially with all the heavy landscaping loading. This is a view of the truncated 3D model for trough design. We use this to help reduce the run times so that we can do iterations and properly get a good design for the troughs, because they were all cast in place and we had to make sure the reinforcement withstood all loads from the landscaping as well as any other loads from the deflections would cause. Now getting into the framing plan more, we ended up initially trying to use the standards that show common K braces for bridges, but from the 3D model, we discovered there's a lot of imbalanced loading, and the diaphragms were seeing much higher loads than anticipated. In the tan color here, we're showing truss support beams because they were in between the main diaphragm lines in yellow here. That the loads that were imparted on these diaphragms were so high that we ended up using HPS 70W steel on them. There were many different types of diaphragms. So we did a lot of diaphragm detailing on here to accommodate utilities. All the ones in yellow were using HPS 70W steel. Not all the diaphragms use HPS 70W. Some of them in the center span, we kept as grade 50, and this is what a typical plate diaphragm looked like there. However, for those areas where the stresses were so high, we ended up using HPS 70W. And the reason being is, as we were trying to design these diaphragms for loads, every time we increased the diaphragm to accommodate loads, we run the model and the extra stiffness would attract more load. And it became a vicious cycle. So in order to break that cycle, using a higher grade of steel allowed us to maintain stiffness as it was. Now, basically, the stiffness wasn't increased, only the strength increased. So we didn't attract more load by doing this. But we still ended up having a beefier connection than just using the 50 grade steel, where these were just attached to one side of a stiffener. These, we need plates on either side of the stiffener, so they were in double shear. And that's how much load we had on these because of unbalanced loading from the surface. Again, these are the trough support beams under each trough. They were attached with shear studs to the troughs. And again, the top one shows a 50 grade steel trough support beam, where the bottom one has a more beefier connection, used the HBS 70W. This is a closer look at a concrete diaphragm, which were placed over each substructure unit. So we had concrete diaphragms at the abutments and piers. What you see in the middle there is a shear block. We ended up using UHPC, those shear blocks, to resist forces. One of the main reasons for that is because we couldn't develop the reinforcement in that short height. UHPC allowed us to get the development that we needed to resist forces, lateral forces. Additionally, we needed to use UHPC in the diaphragm end because, again, we were having problems with getting the proper development length for reinforcement to resist the shear. And the design used the method of shear friction. Additionally, we were finding that we needed to use a lot of reinforcement in these very shallow diaphragms. And some of the diaphragms were seeing tension because of the resistance of the shear blocks as the bridge was trying to expand and contract. So the reinforcement that we used was uncoated corrosion-resistant reinforcement, which was a higher strength. I think also known as MMFX steel in the industry. And this is my final slide. This is showing a bearing orientation plan. There were 6 shear blocks for each substructure unit to resist lateral loads. The bearings themselves did not resist lateral loads. The fixed bearing line then at abutment 2 were transversely guided, so they only resisted longitudinal forces. All other bearings were non-guided bearings, which allowed expansion in any direction. And this allowed the bridge to move basically from the center out. And I'm going to hand it over to Julie.
Thanks, John.
Sure.
So I'm going to reorient us up to the top side of the park, specifically the pavilion and cafe that I'm going to touch on today. Here we have a section through the bridge at the pavilion and the cafe building. The pavilion is the 1-story building that sits on top of the bridge. This is a mass timber building using blue laminated columns and beams, and then cross-laminated timber CLT decking. Adjacent to that and the bridge is the cafe, which has 2 stories below grade and then 1 level above. The level above grade is the same mass timber construction as the pavilion, and below grade we use composite steel construction. And then connecting these 2 elements is a breezeway canopy. The design and construction of the building and most of the elements on top of the park itself or the bridge itself were under a different contract than the bridge construction and will be constructed by a different contractor. So because of this, the building design was on a different schedule than the bridge and lagged the bridge construction. So we started much of our design once the bridge design was well underway. Here we have a 3D section to show another perspective of how the buildings interface with the bridge and how they all interact with one another. Since the buildings are on and adjacent to the bridge, we definitely had some design challenges that weren't common to typical building design. Today, I'm just going to touch on a few of them, specifically related to the pavilion, the one-story building that sat directly on the bridge. And those are building loading, differential movement, and then the bridge troughs that John touched on. So design challenge number one was the building loading itself. So the bridge was essentially, for all intents and purposes, a podium slab for us that our pavilion structure was supported off of. This isn't really anything new. However, the challenge really lied in the communication and coordination between my team and the bridge designers. Since one engineer wasn't really responsible for the total design, any little loading change had to be coordinated back through all the teams and all the different models to make sure we didn't have an issue. This coordination was even more of a challenge because, as I mentioned, the bridge design began work way in advance of the building. So loading assumptions had to be made for what the building was going to weigh and how it was going to distribute load before work even began on developing the architecture around the building. For this, the bridge team assumed a uniform load over the footprint of the pavilion and not localized loads at columns, which is how buildings generally impose their load onto a structure or columns below. Also, my understanding is they assumed that it would be a steel structure, not a mass timber structure, which ultimately ended up being heavier than what was assumed originally. So with all of these assumptions going into the design of the building, we had a lot of work to do working with the architects on what they wanted for the space, and then ultimately what the bridge could support. Architecturally, the space really wanted to have open spaces with as little columns as possible to allow for wide open events, specifically in the front of the building. However, to meet the loading criteria for the bridge, it really wanted the columns to be at 10 to 15 feet on center to allow for a uniform loading. The architects originally were pushing for the pavilion loading and the girders to run perpendicular to the bridge girders, which ultimately put all the load on only 2 of the bridge beams, which wasn't going to work. So there was a lot of back and forth throughout this process where we would propose a column grid, the bridge team would run the analysis, let us know if it was going to work, and then we would go back to the drawing board and adapt and adjust as needed. Ultimately, we ended up with a design that worked, but there was a lot of gymnastics to get us there. So much so that towards the end of the design, we were finalizing solar on the roof of the pavilion, and we were basically told by the bridge team that there was no more additional capacity, even though it weighed maybe 3 PSF more than what we had originally designed into the building. And ultimately, we were able to get the solar to work by doing like a very detailed takeoff of every single dead load on this building to justify it all. But I mean, that's how tight the design was once we were done. Moving into the second design challenge is differential movement. First, I'll start with lateral movement. And as John had discussed, the bridge is moving at its own rate, back and forth based on lateral loads. And then we have the cafe directly adjacent, which is supposed to look tied into the structures that are on the bridge structure. So in order to deal with lateral movement, we introduced an expansion joint as shown in this image at the interface of the breezeway and the cafe. In order to accommodate the architecture, this was a slip connection, so allowing downward load to be transferred at this connection point, but not lateral load, and then allowing for lateral slip. And here's another image of that expansion joint at the interface of the cafe. Laterally, we took all the load from the breezeway and we dragged it back into the pavilion building, and we used shear walls to support the lateral system for that back down to the bridge, which, again, that was another load that they had to consider into the design, along with the trees. Another design consideration was gravity load deflection. Since we are on a bridge, and yes, it's basically just a podium structure, checking for gravity deflections isn't really a new concept, but something that we're not used to dealing with on a typical basis is the camber design that the bridge designs into its girders, and understanding how that movement is going to affect the different components in the pavilion. Also, how adding different components throughout construction is going to affect how the building reacts. So in order to study this, the bridge group provided us deflection output for basically every single load case. So down to every detail of, oh, we added the soil and here are the deflections, and we added the pavers and here's the deflections. And we did a pretty big study to try to understand how every part of the building was going to move in relationship to the bridge. The bridge live load itself, coming from a building engineer, is pretty stringent at L over 1,000. So luckily we weren't looking at very large deflections for live load, over 100-foot long bridge spans. Some of the specific conditions for the gravity load that we were concerned about was the facade for the pavilion. This was a panelized wood curtain wall system. Luckily, the curtain wall system itself was panelized in 5-foot segments. So that did allow for some more movement between jointing, but we did have to detail the slip connection at the top to accommodate all the differential movement across the pavilion, and to ensure that we don't have any cracking once the thing gets built. We also had to look at the pavilion columns to understand how they were deflecting in relationship to the bridge. We didn't have to end up doing any special detailing for the columns. Call it luck, but luckily the way that everything laid out, we didn't have any columns at mid-span that were supporting a girder at the other end that was at 0 deflection, and ultimately we were well within IBC limits for deflection between spans and between column bays. Lastly, we had this breezeway that was supported partly on the bridge at the face of the pavilion, but then also off the canopy over the expansion joint. There was a good bit of movement between the two ends of this, because not only were we on a bridge and then on a structure, but the structure itself actually had to cantilever out to avoid putting any sort of loading onto the bridge abutment. So we had pretty good deflection on each end, and we did have to incorporate movement into the detailing of the connections of these items. And then the last item that I'm going to touch on today for the design challenges of the pavilion are the bridge troughs themselves that John had discussed. So part of the genius of using these bridge troughs was they did reduce the total amount of load that was imposed on the bridge, because as John had mentioned, we have 100-foot, 50-foot tall trees that are going to be planted on this bridge. And as you can imagine, they need a good bit of soil to make the root system work. So instead of building up that much soil on the entire bridge, these trees were put into the troughs so that there was more soil in those areas than the rest of the bridge. And as you can see on this image, the orange denotes one of these bridge troughs, which were at 7 feet on center. How close were they? 12 feet on center. So here's an image of the pavilion ground floor slab with those bridge troughs shown. One of the challenges we had, though, with these bridge troughs was that we couldn't impose any load onto them from our building, because we had utilities running underneath the building and then back into the park structures on the bridge. So we had to design everything to span over top of them, and we had to avoid putting any columns in these locations because they didn't want to take any loads. That was a challenge we had to deal with. I didn't really touch on the park design, but here's an image of the bridge with the park overlaid onto it with all of these troughs highlighted in orange. And throughout the entire design of the park, nothing wanted to structurally put pressure onto these troughs. We had playgrounds, we had hardscaping, and all of these items were designed to span over the troughs. Not so much as the troughs couldn't support the load, but there was a concern that the pressure of items bearing on top of the soil within these troughs would cause for the drainage and the irrigation to be cut off to the trees, resulting in them possibly dying. So there was a lot of gymnastics done on the top side to avoid basically putting any sort of structural loading onto these troughs and spanning everything over top. And with that, I just want to show you a few pictures, courtesy of Kieran Timberlake, the architect on this project. This is looking at the pavilion on your left, your breezeway, and then the cafe on the right. You can see the mass timber is very prominent. I think it's a very pretty building. Looking forward to it being done. And here's one other image, just looking up at the buildings with the some of the park at the front. And with that, I think we have a few minutes left. We can open up for some questions.
All right, great presentation. Thank you very much. I have a few questions in here, so as I read these, if anybody has a question, just put it in the Q&A feature. So the first one, I saw that you had in the diaphragms looking at 70 KSI, and maybe I missed it, but was the 70 KSI investigated for the main beams to reduce any flange thickness?
It was investigated early on, but everything was successfully accomplished using 50 KSI steel. So in the end, flange thicknesses didn't exceed what was industry standard.
Okay. Next question. What was assumed for the diaphragm connection to the girder? Was the connection assumed fully rigid, semi-rigid, and how was that modeled in CSI?
So the diaphragm connections were assumed to take moment. So the diaphragms themselves are meant to be able to withstand moment and provide lateral bracing for the bottom flange. So we had to assume rigidity there. They were very robust. We're talking 3 bolts wide and approximately like 11 bolts high. So yeah, in the model we assumed fixed, and we didn't try to assume any kind of spring coefficient for rotation, because in order to do that by code, you have to basically have enough information to reliably assign a spring coefficient. So they were modeled as rigid.
Okay, thank you. Next question I have here is, will there be a fire suppression system to protect the bridge from vehicular fires? Relevant.
Yes, we didn't show that, but there is. Jesse, you want to mention it?
Yeah, there's a fire protection system spanning under, I guess you can access it from all spans. It'll pass through the diaphragms at each of the substructure units. And also there's a separate feed into the cafe, correct? Yeah, I'm pretty sure. I know there's also a fire department dry standpipe access at the cafe as well. Yes, that was a big part of the project. Emergency management stuff was considered big time, especially in the those conversations only escalated in the wake of Common App.
Yeah, understood. Great. Next question here. At what plus minus temperature sliding of the disc bearings start? Were the temperature forces considered in the transverse direction when the bearings have not slid yet?
So the I understand what you're trying to say. Are you talking about trying to model that in CSI bridge, assume some sort of friction on the sliding surface?
That's what I would imagine the question.
Yeah, those bearings did have a friction coefficient assigned to them in the model, I believe so. That's how we took care of that.
I believe the construction just started, but is it are you ahead of schedule at all?
There were some, as with many of our projects, I think we got hung up in utility work for a while. I can, can't speak for Buckley per se, but I know for sure that they're out there, trying to push things forward as quickly as they can, with a goal to finish this thing ahead of schedule. And I think they're doing a good job of it. I know the Pier 1 that John showed photos of is essentially complete in place. The abutment 1 work that he touched on has been nearly completed. They're looking to actually set the first portion of the girders. You saw in some of those photos, there are multiple field splices. They want to get the first length of it in place, I believe, within the year. They're doing everything they can and being creative and trying to find ways to move this thing forward.
Great. It's 2 minutes after 1. I'll get to one more question here, and then what I can do is I'll put up the PDH certificate, so if somebody needs to jump off, they can get that. So I'm going to share that right now, and if you can hang on, we can answer some more questions, and this way other people can as well. So I'm just going to switch over real quick and share my screen. So right here, if you are interested in the PDH, you can scan that QR code, or you can go to the link right there. And what I can do is I can put that in the Q&A real quick so you can see that link. All right, so while that remains up, I'll ask another question here is what were some of the biggest challenges faced because of the large out-to-out width in terms of transverse movement off the structure?
Repeat that one again for me, please.
Yeah, it was what were some of the biggest challenges faced because of the large out-to-out? So you had all those, all that large cross section in terms of movement. You touched on the shear blocks, but were there any other challenges, or was it, the design went straight to shear blocks, UHPC, and
the
that'll be the
challenges were
design?
definitely that we had to keep the center of the bridge like a fixed region, and shear blocks allowed us to obtain the capacities we needed by using the UHPC. Additionally, all the transverse movement were affecting the utility penetrations through the abutments. So we had to make sure we would be able to accommodate that movement.
I think another aspect that we found as we moved through this was, John mentioned we've got our fixed bearings at the east end, our abutment 2, and we pushed all our movement to Front Street. That ended up requiring a 5-inch. We were able to get away with a 5-inch neoprene strip seal expansion joint there, but we had to do checks to be sure that the spec joint was able to support that transverse movement as well. And we actually ended up wrapping it at the end. We have an approach slab out there and had to provide expansion joints at the north-south limits as well to help with that transverse movement.
Okay, thank you. Next question here. Was there any aspect of design for lighting and or ventilation under the structure? Or did you just get past just under those tunnel limits?
Highway lighting was a big piece of this, and assistance with WSP on a lot of that. As far as ventilation goes, we did not meet requirements to design as a tunnel. We do provide emergency egress at points. Obviously, that doesn't resolve ventilation issues. That was an element that we opted to meet after we discussed it with PennDOT and FHWA. They agreed. There was a system in place. We wanted to maintain it. But no, there were no special ventilation requirements at the length that we had, that 600+ foot width.
Gotcha. And then just to add to that same kind of concept, anything with emergency evacuation?
Yeah, so just mentioned, we maintained emergency egress points. There will be doorways through the 2 piers. Sorry, there will be a doorway through Pier 1. There's an emergency existing access point at Pier 2 because 95 drops down in grade below Christopher Columbus Boulevard at that south end. There was an emergency hatch with a ladder that we were able to maintain, luckily. Meeting ADA requirements there is obviously very tricky. We know that people will hopefully have the ability to walk out one end or the other in an extreme emergency situation. So that was a consideration and accounted for somewhat, but still in the abutment 1 bay, that ramp and southbound 95. We also maintained and retrofitted an existing stairway access point with a hatch at Front Street level.
Great, thank you. I believe, so for this structure, it's considered a bridge then for inspection reporting to FHWA, or is there any tunnel inspection requirements?
Yeah, it's coded as a bridge. It'll be inventoried by PennDOT as a bridge. You know, till it's built, we won't quite cross the coordinating inspections threshold, but I know it's one of our closeout pieces. We'll have to get that teed up.
Great. For Julia, what software was used for the mass timber structures?
So we used mostly RAM elements in combination with spreadsheets, and then the connections themselves were actually designed by Thornton Tomasetti as a sub to us, since they have a lot of experience in that. Typically, on some jobs, you would delegate that into construction, but because architecturally we were looking for a certain look, we wanted to get that all detailed up front. So we did that all as part of the contract drawings with their assistance.
Great. Question here was just thank you very much. Looking forward to the project being completed. Another question here. What is the UHPC loading in the pedestrian section shown in the design load table early in the presentation? I think I'll stop sharing if you want to jump back to that slide, if you wanted to share again.
Yeah, let me see if I can get us back to it. See if this comes up. We got to scroll way back. Let me restart. Yeah, I'll just do it from the get-go because it was fairly early on. Apologies for the scroll time, everyone. So it's the worst part, huh? It's into here is by a couple, right? Yeah. I'm not sure what the UHPC on the design region table. I assume that was what we were looking at. That was the couple. Gets a reminder.
There you go.
Oh, here, UHPC
160.
load. I see.
Well, I guess the question is, what is that loading?
That have been for the
That's just that's the UHPC itself.
Yes.
Okay.
Yeah, I think we broke out the UHP separate from the other. So these are the unit loads for it, right?
I gotcha.
For 0.515, that's your 150 PCF standard load for, you know, concrete on a bridge. The UHPC carried a higher unit weight, and that was just what was represented here.
Okay, makes sense. Next question is, what are the reason for the different rock socket lengths for drilled shafts?
Yeah, we peppered this site with borings. This is really a better question for our geotech sub Aegis, but the rock profile throughout here, as well as, you know, obstructions that we hit, it just, as we went north, because we're, you know, reminder 600 plus feet wide here, the conditions varied a lot, especially along the waterfront. Probably, there you go. What we were finding is at the south end, it should be at the south end. Yeah, okay. The box culvert there helps orient. At the south end, the rock profile was just deeper. And the difference between that case on the rock socket and some of the deeper rock socket lengths was because there was some weathered rock encountered at the surface for some layers.
Right. And last question here. Are the building foundations anchored to the deck or separate? Are the trees tied down to the deck, or were the troughs assumed to provide the support?
So the pavilion itself is attached to the deck where we're using post-installed connections and essentially pouring like a strip footing around the pavilion that's being anchored. As for the trees, I think there's a ballasted type system, and Jesse, maybe you can speak more to that kind of ballasts it down to the troughs, but I don't think there's any like anchorage, like mechanical anchorage between the two.
There's a large anchor plate underneath the root ball.
Yeah.
But it wasn't physically attached to the trough.
And it's not intended to be. And not something we touched on in this presentation much, but we have a very robust waterproofing system spec'd for this, particularly in the troughs, to help prevent the roots deciding that they do want to be part of the trough in the future.
Gotcha. Well, I have one last one. This is a pretty amazing project. Kudos to your team. Working on this. So you had horizontal structure, vertical structure, and you had architects. So of the bridge engineers, the architectural engineers, and the architect who tended to get their way the most.
Just no comment this one. Okay.
Yeah, I mean, I think that we had a healthy back and forth on a lot of issues. I mean, ultimately, we wanted it to look great because that's why people are coming down there at the end of the day. But there was only so much the structure could do. So I think there was a lot of push and pull. I think ultimately it looks the way that I think that the landscape and architectural team ultimately wanted it to look like. Maybe they had to make some concessions, but ultimately I think the product was what was, presented at the beginning and the renderings when everything started.
There were a
Great
lot of
answer.
conversations that started with, no, we can't do that. But okay, let's talk about it. Okay, maybe we can do that.
So if you come to the social next week, we'll get you one drink ticket, and then you can really tell me the true answer then.
Julie's answer was spot on.
Well, with on behalf of SEI, and everybody attending, thank you so much. This was a great presentation. We definitely learned a lot here. So I know we went a little bit over, but I think that was worth the extra 13 minutes here. So again, thank you very much for attending. And if everybody wants to ask more questions, come on out next week and to the social.
If we may, Mike, I want to thank you all again for hosting us. Thanks everybody for the engagement with questions. Try not to overwhelm with shout outs here, but from the bridge perspective, did want to give a quick shout out to two other folks who weren't represented on here, but Carl Oberg and Clayton Van Berth, both former Pannoni employees at this point, but integral to the bridge design and development. Not sure if they're on, but they're out there, and really appreciate their help through all of this as well.
Great.
Along with many others, we could do names all day, but thank you.
All right. Well, with that, always reach out and we can talk again. So thanks everyone, and have a great rest of your week.
Thank you.
Thank you.
Thank you.